Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve material nonlinear, especially an elastic, perfectly plastic material using tangent modulus. We can say it as a bilinear handling. In ANSYS, they will call it bilinear. Similarly, bilinear handling we are going to do. So up to this elastic limit, it will take Young's modulus and Poisson ratio. The yield strength of the material is 235. After that, we are specifying that if strain increases, the stress will not increase. The stress will be same 235 megapascal. That is the way it will do. This case we are going to solve using code aster. I have taken a simple geometry of a cantilever beam. One side I am fixing it. It has the section I am specifying here. So I'm going to model it, and here I'm going to apply a force of minus 155 kilonewton. The simple model I have taken. I'm going to solve this model using code aster, and the stress value is around, the displacement is 23 mm, 23.625 mm. This is the value we'll be getting. Now we'll do the analysis using salome. So this one is the bilinear handling we are going to do using a tangent modulus value. Geometry model. This is simple actually. We are going to model this using a simple box primitives. Any direction we can take it. I'm going to take it as x direction as a length. The length is 2000 mm, that means 2 meter. X is 2. B. Y is actually 2h. 2 into h is 200. That means 0.2. And x value is 0.14. Now you can see, no, actually we need to modify it. This is 0.14, this one is 0.2. Yeah, this is our model. See, yes. So now just apply and close. So only 2 groups, create a group. Here we need to fix it. Here we need to apply load. Just apply and close. This only 2 groups we have. We can save this file. I have saved it. Now just go to the case. Young's modulus 210 gigapascal and Poisson ratio is 0.3. Now we will go for meshing to create the mesh. Mesh, create mesh. We can go for X mesh also. 2D it is a quadrangle mapping. 1D it is actually Y discretization. Local length 0.03 I am giving. Just save OK. Apply and close. Right click, compute. We have created very good X mesh. Now we'll check the groups. Yes, it's fine. Now we'll take this file for aster study. Now I'm just saving this file. Now we'll create the setup one by one. Add a stage. Go to mesh. First read the mesh. Mesh 1. MAD format, just apply and OK. everything is similar, only thing is the material property where we are specifying, there only a small modification we have to do. Go to model definition. Everywhere it is a mechanic 3D model, just say OK, apply, OK. Second one is material. Yes, here we need to define the material. Linear isotropic, Young's modulus is 210 gigapascal, Poisson ratio is 0.3. 210 e power 9, this is 0.3. Just say OK. There is one more thing is called, there are different properties we can specify it here. There is an option called acro line. This is to specify the tangent modulus. So acro line, if you want to specify it as a function, means acro line FO. Traction is nothing but we can give an input as stress strain curve. So acro line, just go edit. Here two things it will show. One is T sigma epsilon is nothing but tangent modulus. The tangent modulus is 0, and yield strength of the material. Yield strength of the material is 235 megapascal. So 235 e power 6. Just say OK. Just apply it. Now you can check it here. Young's modulus, Poisson ratio is a isotropic material, that is coming Elasto. Acro line is the property to specify the plastic regions. Tangent modulus we have specified 0 and yield strength is 235. Now we have defined the material, just apply and OK. Now we need to assign the material to the model. Assign a material. Everywhere. Just say OK, just apply and OK. Now functions. This is we are going to do with a non-linear static analysis. The static non-linear solver we are going to do. Instead of applying a ramp load, we are going to apply incremental load. For that we are going to use a function, multiplication function. So define function, coordinate with a time. Here it will show time. Just edit. When time is 0, the load is 0. When time is 1, the load is also 1. Linear increment we are going to do. This is the way we are going to increase the load linearly. Just say OK. Just apply and OK. This is, I'm just going to rename it as load F multiplication function. Then we need to specify the instant also. Defill list real. Debut is nothing but start. Until 1 we need to run, and step is 0.1. 10 iteration we have to do. And then one more is defill list inst. This is just a method of doing iteration. Just OK. Just apply and OK. Now we have specified the functions and time period. Now we can go for boundary condition. Mechanical load, one side we have to fix it. Group of element, fix, blockage, displacement, save OK. Other side we need to apply (155 kilonewton) we need to apply. So in this PPT also we can check minus 155 kilonewton. The only thing we don't have any force load boundary condition. We have everything is a pressure boundary condition, as we have seen in the previous analysis. just go to boundary condition, assign a mechanical load. There is option called force space. Force space. This also be a pressure boundary condition only. Convert your force into pressure. Group of element, load. We need to apply in z direction. Functions. The force I need to apply it. So 155 into this area minus 155 kilonewton 12330 multiplication with the area of this model 0.14 into 0.2 0.14 not multiplication divided by area divided by 0.14 into 0.2. So this is the value, this is the force value for this space, I mean this is the pressure value for this space for the force of minus 155 kilonewton. So we are just converting that force into pressure, we are applying it. Just apply, just close it, just OK, just apply. F is at force variable here, just OK. Now we have applied this force also to boundary conditions. Now we need to define the solver. Go to analysis, statics. There is a solver called static non-line. Time stepping, we need to choose this one, just say OK. Just one by one you come loads, switch on this loads. There are two loads. First one is load, say OK. Second one is load 0. Multiply with the multiplication function. Save. When the time is 0, the load is 0. When the time is 1, the maximum load will be applied. It will increase one by one. There is no contact. Need not to change anything here. If you want to specify, we can specify it here. It will take default value, just leave it default. Here we can choose it, which one we want to use. There are different model is there, relation, Von Mises isort line, we can go for petite crowd GDP, anything. Just OK, just apply, say OK. Now we have defined the solver. Now we can go for saving the output. Choose the location, specify the name. I'm just giving result 123.rmed. Say OK. Here you just go here, edit. Now we can choose stress also. Directly you just go to post processing, call champ, reuse the input, sigma elno, sigma node, criteria, SAEQ elno, SAEQ node. Just check the output. Instead of static null, call champ we need to use tau champ, make it yes. Just OK, apply and OK. Now just save the file. just run it. Give some more memory. Just save the file, just run the keys. We have to watch on this message file. If any error comes, we need to modify it. Now we have chosen von Mises isotropic hardening. Oh, it is solved very nicely and without any error and given the result. Now we can go for post processing. Pictures, code aster, elastoplastic. I have given name as result123.rmd. Just open it. Now you can see all the results are came here. Just OK. Now just choose displacement. Z direction I have applied with Z. We can run it. Now just change this value. I can go into the displacement. Now see the deformation. Give some scale factor, apply it. Yes. So this has to be bent like this in Z direction. So maximum displacement is -22. Sorry. We are getting 22 mm. We can check the result here. It's coming around 23 mm, 1 mm variations. By increasing mesh size and changing the order of element, we can achieve this value. Now we can check the von Mises stresses. Just go to here, SIEQ node, change this into von Mises. We are getting maximum stress of 260 megapascal. So here we are getting tensile, here we are getting compressive. This is, we can view it in von Mises signed. See, 260 megapascal tensile, 260 megapascal compressive. Now we can animate this also. We can loop it. This is very quickly it's animating. For that we can set the animation track with number of frames. We can delete. We can increase the number of frames. So now we can animate. That is, we will see in the next tutorial. So this way we can animate it. This one is the stress stress, and here this is the directional stresses. Sigma x, sigma y, sigma z. We are getting maximum stress in sigma x, 430 megapascal we are getting. So this way we can animate it. For better view this color, instead we can go for this color also, blue to red rainbow. Make it in this into 12. In that we have completed of doing a nonlinear material analysis in aster. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.